A-level statistics, displaying data in histograms. Let's have a look at what we mean by a histogram. Now, histograms are used to display continuous data, but first we must group it. For example, suppose the weights measured in kilograms of 10 children, when rounded to the nearest kilogram, are listed below. As it stands, we could group the data into the following groups: 40 to 49, 50 to 59, 60 to 69. Now, once rounded, all the data would fit into one of those groups. However, the unrounded weight of 50 kilograms could be 49.8 kilograms, and so the child's actual weight would fall between the first two groups. If the numbers have been rounded, then for the unrounded data, the classes should be 39.5 up to but not including 49.5, from 49.5 up to but not including 59.5, and 59.5 up to but not including 69.5. We can show this on a diagram, and we see that there are now no gaps between the groups. Now, this is a requirement. To draw a histogram, we must ensure there are no gaps between the groups when grouping the data. However, the groups do not have to have all their widths the same. So we can group the data that we now have in a table. In the first group, the number must lie between 39.5 and 49.5, and that means it's all the numbers that are in the 40s. And there are 1, 2, 3, 4, 5, 6, 7 of them. In the second group, the numbers must lie between 49.5 and 59.5, and so all the numbers are in the 50s. And there are 1, 2, 3, 4, 5, 6, 7, 8 of them. And in the last group, the number must lie between 59.5 and 69.5, and there are 1, 2, 3, 4, 5 of them. Now, in this case, the bar width or class size of each group is 10. Now we can see that the size of the first group is 49.5 take away 39.5, which is 10. The size of the second group is 59.5 take away 49.5, which is again 10. And the third group, 69.5 take away 59.5, which is also 10. Now, in a bar chart, the height of each bar represents the frequency, but this isn't the same in a histogram. In a histogram, the area of each bar represents the frequency. Now, usually the area equals the frequency, but sometimes a scale is introduced. So, if the area equals the frequency, that means the bar height times the bar width is equal to the frequency. So the bar height is the frequency divided by the bar width. Now, on our table, we can work out the bar heights. It's the frequency divided by the class size. So that's 7 divided by 10, or 0.7, 8 divided by 10, which is 0.8, and 5 divided by 10, which is 0.5. The bar height is also called the frequency density. Now let's just review what we've done. We've been given a list of children's heights. We've decided on some classes that we can divide it up into, and we've made up a table. We saw that the bar height was equal to the frequency divided by the bar width, or the frequency divided by the class size. We named the bar height as the frequency density, and we can now draw a histogram of the children's weights. The weights are drawn along the x-axis, so the x-axis has to stretch from 40 to 70. Now, because it's not starting at 0, we draw a short zigzag line to show that the region of the graph from 0 to 40 has been compressed up. Now, the frequency density is drawn as the y-axis. In this case, it just goes from 0 to 1. The first bar stretches from 39.5 to 49.5 and has a height of 0.7. The second bar stretches from 49.5 to 59.5 and has a height of 0.8. and the third bar stretches from 59.5 to 69.5 and has a bar height of 0.5. Since the bar height or frequency density is equal to the frequency over the bar width, the frequency is measured as the number of children and the bar width is measured as the number of kilograms, we have that the bar height or frequency density is measured in children per kilogram. Now if we took the bar width or class size as 5, then a unit of weight would be 2 kilograms. So the frequency density would be children per 2 kilograms. In which case the first bar height would be 7 divided by 5, which is 1.4. The second bar's height would be 8 divided by 5, which is 1.6. And the last bar's height would be 5 divided by 5, which is 1. Now we could draw these onto a graph which would have to have a height of about 2, and we could draw in the bars with height 1.4, 1.6 and 1. The graph is now taller and it's easier to read off results more accurately. Let's have a look at another example. At a vet surgery in 1 week, 60 dogs were weighed in kilograms, and the sorted results are shown below. In part 1, we're asked to group the data in the following groups. The weight goes from 5 up to but not including 10, from 10 up to but not including 15, 15 and up to but not including 20, and 20 and up to but not including 30. Well, to solve this, we first need to draw a table. We then need to see how many there are in each group. In the first group, 5 to 10 kilograms, we see there are 9 dogs. In the second group, 10 up to 15, we see there are actually 25 dogs. In the third group, 15 to 20, we see there are 18 dogs. And in the last group, 20 to 30, we see that there are 8 dogs. Now we can fill in the rest of the table. In the first group, we see that the class goes from 5 to 10, so that's a class size of 5. In the second group, it goes from 10 to 15, so that's a class size also of 5. In the third group, the class goes from 15 to 20 kilograms, so that's a class size of 5 kilograms. And in the fourth group, the class goes from 20 to 30 kilograms, which is a class size of 10. Now, because it's a histogram, the bar height is the frequency divided by the class size. So in the first row, we have 9 divided by 5, which is 1.8. In the second row, we have 25 divided by 5, which is 5. In the third row, 18 divided by 5, which is 3.6. And in the last row, the class size is 10, so the height is 8 divided by 10, which is 0.8. We can then draw these on a histogram. Now the weight is drawn along the x-axis, so it has to go from 5 up to 30. Because we're not starting at 0, we can draw a zigzag pattern just after the 0 to show that 0 to 5 is compressed. Then the frequency density is drawn in the y-axis, and the largest number we have is 5, so we need to draw the y-axis slightly higher than 5. And then in part 2, we're asked to draw the histogram. So we draw the first bar stretching from 5 to 10 with a height of 1.8, the second bar stretching from 10 to 15 with a height of 5, the third bar stretching from 15 to 20 with a height of 3.6, and the last bar stretching from 20 to 30 with a height of 0.8. Now in part 3 we're asked, from the histogram, estimate the number of dogs with weights between 13 kilograms and 26 kilograms. Well, to do this, on the graph, we draw a line vertically upwards from 13 kg, and we draw another line vertically upwards from 26 kg. Now we want to work out the area of the bars that lie in between those two lines. Now we have 3 areas which we can label as A, B and C. And so the area of A plus B plus C is equal to 2 times 5 plus 5 times 3.6 plus 6 times 0.8. Now that's 10 plus 18 plus 4.8, which is 32.8. Now since we can't really have a fraction of a dog, our estimate is that there are 33 dogs between the weights 13 and 26 kg. Now in part 4 we're asked to check this from the raw data. Now if we look at the dogs that lie between 13 and 26 kilograms, we see that there are in fact 35 of them. So our estimate of 33 is quite close, although not exact. Let's look at one more example. In a paper aeroplane competition, the idea was to stay in the air as long as possible. The time of flight was measured in seconds for each plane, and the results were drawn in a histogram. Now 6 planes crashed straight into the ground, so they lasted in the air less than 1 second. In part 1 we're asked how many planes were there altogether. Well, to solve this we see the area of the first bar is 6 times 1, which is 6. And there are 6 aeroplanes, so an area of 1 represents 1 aeroplane. So the total number of aeroplanes is equal to the total area, which is 1 times 6 plus 1 times 7 plus 1 times 10 plus 2 times 7 plus 3 times 5 plus 4 times 4 plus 4 times 2 1/4 plus 4 times 1/4. That is 6 plus 7 plus 10 plus 14 plus 15 plus 16 plus 9 plus 1, which is 78. So the total number of aeroplanes is 78. Now in part 2a, we're asked to calculate an estimate for how many planes flew for between 2 and 6 seconds. Well, to do this, we draw a vertical line up from 2 seconds and another vertical line up from 6 seconds. And we want to find the area of the bars between those two lines. Well, this gives us 1 times 10 plus 2 times 7 plus 1 times 5. That's 10 plus 14 plus 5, which is 29. So 29 aeroplanes flew for between 2 and 6 seconds. In part B, we're asked calculate an estimate for how many planes flew for 10 to 15 seconds. We draw a line up from 10 seconds and we draw a line up from 15 seconds. Now we want to find the area of the bars between those two lines. Now that is 2 times 4 plus 3 times 2 1/4, which is 8 plus 6 3/4, or 14 3/4, and so we would estimate 15 planes flew between 10 and 15 seconds. Now in part 2c, we want to calculate an estimate for how many planes flew for longer than 7 seconds. So we can draw a line vertically up from 7 seconds and then work out the area of the bars that lie in the region above 7 seconds. And that is 1 times 5 plus 4 times 4 plus 4 times 2 1/4 plus 4 times 1/4, which is 5 plus 16 plus 9 plus 1, which is 31. So 31 planes flew for longer than 7 seconds.